Okay, welcome back to conformal invariance. Let me start by making a couple of remarks about a proof from the last class, and also a few words about curvature. And then we're going to start discussing a new topic, which is capacity, or the measurement of the size of a compact subset of the complex plane using techniques that are related to harmonic analysis, complex analysis, and potential theory. Okay, so the first remark I want to make is about a theorem that we discussed last time, which was that if f from the upper half plane to C is analytic, and f of z and bounded, and f of z tends to a along a path gamma, then f of zn tends to the same value a if zn goes to infinity in the upper half plane, of course, and it stays away from the real axis. So say pi minus alpha is less than the argument of z is greater than the argument of z is greater than alpha, which is greater than 0. Okay, so the picture was we have some path, and along this path, f is converging to this constant a. And then we have a sequence, Zn, and we know that Zn lies within some sort of pi slice, so that it doesn't get too close to the real axis, and it's going off to infinity. And we want to say we have the same limit along this sequence as we did along this sequence. And it's easy to reduce to the case where the f is tending to 0. Just subtract the constant a from f. And of course, we can also assume that f is bounded by 1. It's bounded by something. And then what I discussed last time was a way to prove that if f is less than epsilon along gamma, then it's less than some function of epsilon along Zn, where that function depends on alpha. But that doesn't complete the proof, and I just want to remark on how you complete the proof. So the problem is that f might start out being relatively large on gamma. It's only once it's beyond a circle of some radius, say r, that we can assume f is less than or equal to epsilon on gamma. And then everywhere else it's less than 1. And what we want to show is that when you're at one of these points Zn, then the influence of gamma on the value of Zn is very significant. So that tends to make the value at Zn small also. And the influence of f and the rest of the upper half plane has small influence. And one way to do that, this is the step that I omitted because we were running out of time, is very simple. What you do is you make a change of coordinates. Z goes to z plus r squared over z. And what this does is it takes this circle and it flattens it out onto the real axis. In fact, if z is equal to r, this goes to r plus r squared over r. So it goes to 2r, and the other end of the circle goes to minus 2r. This is one of our favorite conformal maps. So you replace everything you're studying with its image under this map. And you just consider the part of the path that that's left the circle of radius r, never to return. And that transforms to a new path here. So we get a new gamma, and we get a new sequence of points. Maybe I'll call this gamma hat. And we get a new sequence of points, Zn hat. And we get a new function, f hat. And the advantage is now f hat is less than or equal to epsilon along this arc. But what about the Zn's? Are they still trapped inside this cone? Well, the point is we have a simple formula for Zn hat. It's just Zn plus r squared over Zn. And since Zn is going to infinity, this term matters very little. So the argument of Zn hat is asymptotic to the argument of Zn. In other words, they're equal up to an error which tends to 0 as n goes to infinity. And so even though the Zn's at the beginning might not be in this cone, they're eventually within a cone of the same angle. And as a consequence, the proof that I gave before, which assumed that f was less than or equal to epsilon along the whole arc, then can be used to show that once epsilon is equal to 0 along this red arc, you change coordinates, you can conclude that along this sequence, the limit is bounded by a constant going to 0 with epsilon. And since epsilon was arbitrary, that finishes the proof of the theorem that Fn of Zn also goes to 0. Okay, so that was just a remark on a important but step in the proof of this theorem. The second remark I want to make is about the Laplacian. So maybe I'll erase this. So we've been advocating the point of view that when you have a function, we call it phi, on a domain omega to r, that one should really look at the Laplacian of phi dx dy. This is something more like a measure. In fact, this can be thought of as d star d of phi. It's really a two form. It's something that you can integrate over a region. So how do you get a Laplacian that goes from functions to functions? So if we want a Laplacian that goes from functions to functions, we have to have more information. The conformal geometry of the region determines a Laplacian that attaches a two form to any function. So we need some way to convert that two form back to a regular function. And the additional structure that's needed is a metric. And so if we have a conformal metric, then we can define the Laplacian of a function in that metric to be another function. And the way it's defined is the Laplacian in that metric of phi is equal to, in local coordinates, the ordinary Laplacian of phi divided by rho squared of z. And so if you like, what you do is you take the Laplacian thought of as a measure, Laplacian of phi dz squared, that only requires the conformal structure, and then you divide by the area form coming from your metric. So you compare this two form to this two form, the one coming from your metric, and you take their ratio, and that gives you a quantity that is now a function. And that's how we define the Laplacian on functions. It requires the choice of a metric. And the fancy way to write this Laplacian would be star d phi. In other words, division by the volume gives a Hodge star operator from two forms back to functions. And that allows you to discuss, for example, eigenfunctions of the Laplacian. You can't have an eigenfunction when you have an operator from one space to a different space. But when you have an operator from one space to itself, then you have eigenfunctions. So for example, let's take our domain omega to be the upper half plane. Let's take rho to be the hyperbolic metric, dz over y, or z is x plus iy. And I claim that the function f of s of z is y to the s is an eigenfunction of the Laplacian. In fact, it satisfies the Laplacian in this metric of f of s is s times s minus 1 times f of s. So this is an eigenfunction. And similarly, when we have domains in In the plane, we might impose zero boundary conditions and try to diagonalize the Laplacian in terms of eigenfunctions. This can in fact be done on suitable domains in the plane. But in any case, what does this quantity mean? Let's just check this. So we have the function y to the s. The Laplacian with respect to this metric is nothing more than the second derivative with respect to y of y to the s. That's the Laplacian of fs. And then we have to divide by rho squared. So we need to divide by rho squared. Rho is here. Rho squared is 1 over y squared. So we put a y to the minus 2 on the bottom. And now we differentiate twice upstairs, and we get s minus 1, y to the s minus 2. But the metric also has a y to the minus 2 in it. These two cancel out, and you get s times s minus 1 times our original function fs. So that's a typical calculation with the Laplacian with respect to a given metric. It's not very hard because the calculation you have to do is just the ordinary Laplacian, and then at the end of the day you do this algebraic operation, you divide by the area form of your metric. And finally, I want to mention how curvature can be expressed with respect using this Laplacian. So if you like, this is a definition, but it agrees with other definitions. The Gauss curvature of a given conformal metric rho is given by k of rho is minus, and now you do something sort of incestuous. You use the rho Laplacian and you apply it to the function log rho. And out will come a number. And it will vary from point to point, and what that number is telling you is the sectional or Gauss curvature of this Riemannian metric. So let's do an example again. We'll use the same metric in the upper half plane. If rho is equal to z squared over y, then so by log of rho, what I mean here is you write rho as rho of z, dz squared. And then log of rho will just mean you take log rho of z. So rho of z is 1 over y. So the curvature of this metric, which we hope is minus 1, should be minus the rho Laplacian of log rho. So the rho Laplacian is, so this is minus the Laplacian of the log of rho. Rho is 1 over y. And then all divided by rho, because this is the rho Laplacian. So divided again by rho squared rather. So divided again by y to the minus 2. Okay, so let's just compute that. So on the top, this is the same as minus log y. So we get two minus signs. So we get the second derivative with respect to y of the logarithm of y, divided by y to the minus 2. When you differentiate once, you get 1 over y. When you differentiate again, you get minus 1 over y squared. So we have minus y to the minus 2 over y to the minus 2, which is minus 1. So that verifies that the metric on the upper half plane is in fact a hyperbolic metric of constant curvature minus 1. Okay, now here's a little remark. When you make a change of coordinates, let's recall how the metric changes. If you pull back a metric by an analytic map, you get a new metric which is given locally by rho of f of z times the absolute value of f prime of z times the absolute value of dz. and its curvature should not change. That is, we should have that the curvature of F upper star of rho is the pullback of the curvature of rho. That's the statement that this is an intrinsic invariant. So for example, if this metric has curvature -1, so should this metric. But look at how sorry, this should have been rho. Look at how the function defining rho, the metric changes. It changes by multiplication by the absolute value of f prime. So when we do this calculation in the new coordinates, we're hoping to get the same result. But what we've done is we've taken the log of rho and we've changed it to the log of rho of f of z times the absolute value of f prime of z. And you might wonder, doesn't this absolute value of f prime of z mess things up? But it doesn't. And the reason is that the Laplacian, that the logarithm is then the sum of the log of these two terms, and the Laplacian of the log of f prime is equal to 0. That's the real part of the log of f prime, so it's a harmonic function. So when you change coordinates, you get an additional factor of f prime, but it does not change the curvature because of this calculation. And I should mention that if you were on a higher dimensional complex manifold, you could do something very similar, but instead of rho, you would take here the determinant of your metric. Say if you had a Kähler metric, you could take its volume element and then take the Laplacian with respect to the given metric, its log, and you would get, instead of the Gaussian curvature, you would get the Ricci form of the metric in higher dimensions. Okay, so that's how curvature relates to the Laplacian, and that's how we can turn the Laplacian on measures into a Laplacian on functions. Well, there's more to say about curvature. Maybe I'll finish with just one little remark. Which is that it's very nice often to think of curvature as a measure. So it's nice to use Laplacian log rho equals mu as a two-form or measure recording curvature. Or to put it differently, what's often useful is to take the curvature of rho, but then multiply this by rho squared. That's equivalent. So often you see the combination of the curvature and the metric. And a good example of this is the Gauss-Bonnet formula, which says that, for example, on any closed surface, call it sigma, we have that 2 pi times the Euler characteristic of sigma is given for any metric by the integral over sigma of the curvature of that metric with respect to the area form of the metric. And if you like, you could just, if these are Riemann surfaces and everything is conformal, you can think of this as the integral over sigma of, up to a sign, sorry, this should have a minus sign in it, of minus the Laplacian of log rho. And the reason this is a useful way to think about things is that there are examples of metrics where the curvature is all concentrated on a finite set or on a one-dimensional manifold instead of being spread out over the surface. So for example, if sigma is the Riemann sphere, so it's a two-sphere, we think of it as the Riemann sphere, and we give it the spherical metric, rho of c hat, then the curvature is identically equal to +1. And 2 pi times the Euler characteristic is 4 pi. And that's the integral of +1 with respect to the spherical area. In other words, that's just the area of the sphere. And of course, the area of the unit sphere, or the sphere of curvature +1, is indeed 4 pi. In general, 4 pi r squared. So that's an example of the Gauss-Bonnet formula in the case where the metric is smooth. On the other hand, if you take a triangle with the internal angles alpha, beta, and gamma, then it turns out that if you take 2 copies of this triangle and glue them together, you get a topological sphere. And it has a metric on it. And the metric is flat. So doesn't that contradict Gauss-Bonnet? Well, it doesn't. If you think of the metric, if you think of the curvature rather as a measure, it turns out that the curvature, which can be calculated, by the way, using the Laplacian, thinking of it as a distribution, the curvature turns out to have delta masses at these 3 points. So let me be somewhat formal here. We take the double of t, let me call that sigma. It's topologically a 2-sphere. And it turns out that the curvature at one of these cone points is equal to the angle defect. In other words, normally at a point, you expect the total angle around the point to be 2 pi. But when you take this cone point and you double it, the total angle around that point is 2 alpha rather than 2 pi. So the angle defect is 2 pi minus 2 alpha. And notice that that's positive because alpha is less than pi. And then when we apply Gauss-Bonnet, we get the integral of the curvature, now thought of as a measure, over this surface is equal to, well, we have 2 pi minus 2 alpha. So we get 6 pi minus 2 times alpha plus beta plus gamma. One contribution from each of the 3 cone points, and this should be equal to 4 pi. And so that shows there's a relationship between the 3 angles of the triangle, namely, this quantity has to add up to pi. And so the fact that the vertices of a triangle have internal angles summing up to pi is an instance of the Gauss-Bonnet formula. And it shows the utility of thinking of curvature as a measure. Okay, here's one final example. If you've ever made pancakes, you might have noticed, if you're a topologist, that a pancake is a sphere. It's just a very flat sphere. So as an extreme example, we might imagine taking the unit disk with the Euclidean metric and taking another copy of the unit disk with the Euclidean metric and then just gluing them together along their boundary. And the result, well, this should really have 0 width, but you can think of it as sort of a pancake. In any case, it will give a surface, which is a 2-sphere. But the metric on the surface coming from the disk will be flat on the top of the pancake, and it will be flat on the bottom of the pancake. The curvature will be 0. So where is the curvature? Well, the curvature results from gluing together the top and bottom of the circle. So when you have a circular arc and another circular arc and you glue them together, the resulting metric has curvature diffusely spread out along this one manifold, the seam, after gluing. And it turns out that the amount of curvature, if this has curvature, geodesic curvature K1, this is geodesic curvature K2, the curvature becomes the measure K1 plus K2 times arc length along the boundary. So notice that, for example, if you glue along straight lines, then the geodesic curvature is 0 on both sides. When you glue together, you don't get any curvature. If you were to glue along concave curves, you would get negative curvature along the seam. And this is actually used in sewing or tailoring. When you want to make a suit and it needs to have some negative curvature, like under your arm, or if you want to introduce some positive curvature some way, you do it by taking cloth, cutting it along a curved line instead of a straight line, and then sewing it together. And it creates diffuse positive or negative curvature along the seam. And so here, when we glue the disc to itself, the curvature on the top boundary, the top unit circle is just 1, which is the same as the curvature on the bottom unit circle. So when we glue them together, the curvature becomes the measure 2ds on S1. And when we integrate 2ds over the circle, well, the circle has length 2 pi, so we get 4 pi, which is what we expect. 2 pi times the Euler characteristic is always the integral of curvature when you have a metric on the sphere. Okay, so there's much more to say about curvature, but in the interest of time, I'm going to go on directly to the next topic, and I urge you to look in the notes to see a little bit about this beautiful idea of an ultra-hyperbolic metric, which was introduced by Alfors, and is very useful in many settings in both one complex variable and several complex variables. Okay, so any questions on this brief excursion into more uses of the Laplacian and its relation to geometry? Okay, so I have an interesting question for you. It concerns a compact set contained in the complex plane. And the question is, how can we measure the size of K? So we want our measure to have the following property. We want that the size of K, or let me call it S of K, has the property that if you take the set K and you scale it, then the size goes up linearly with the scale factor. Okay, so who can propose a way to measure the size of an arbitrary compact set in such a way that it scales correctly under dilation?
One suggestion is looking at the diameter.
Yeah, right. So one idea is just take the diameter. So an example of a size that works is the diameter of K. And what is the diameter of K? It's the maximum over pairs of points, A1 and A2 and K, of A1 minus A2. Now the problem with the diameter, I like the diameter, but the problem is that it's sensitive only to the 2 most distant points in K. And if we vary some of the intermediate points, then the diameter won't change. So it's not really looking at all of K. So I want something like the diameter, but that brings all the points of K into play. So for example, what is something that we could do if we want to consider triples of points in the set? What might be a substitute for the diameter that involves 3 points rather than just 2?
Take the average of the distance of all 3.
Right.
Each pair.
Right. So one interesting idea is you could take the average of the distance of 3 points. 3 points form a triangle. And you could, there's various things you could do. You could take the square root of the area of this triangle. You could take the average of these lengths. But here's a third proposal, when we have 3 points, we can also look at A1 minus A2 times A1 minus A3 times A2 minus A3. We can take the product of these 3 distances, and we could call that a new kind of diameter of the set. Let me call that the 3 diameter, sorry, D3 of the set K. And it will be, of course, it won't be this exactly, it will be the max of this product over all possible triples with AI and K. Okay, so that's pretty good. That uses more points in the set, but it has a defect. Its defect is that it doesn't satisfy this property. If you scale the set, all 3 of these terms will multiply by lambda. So this will be homogeneous, but of the wrong degree. It will scale by lambda cubed. How can we rectify that?
Just
If you have a
raise
function, yeah, go
raise to 2/3.
yeah, or maybe to the 1/3. So we have 3 terms here, each of which scales by lambda. So if we take the cube root of that product, it will scale by the first power of lambda. So good. So more generally, we can let, and now this will be a definition. We let dn, and formally this is dn of k, but usually k will be fixed, so I'll drop the k. We let this be the maximum over a1 up to an in k of the product over all pairs I less than j of the absolute value of ai minus aj. And then we're going to let little dn of k, big dn of k, and then we have to fix it by the number of terms in this product. So how many terms occur in this product? Well, there's A1 gets paired with n minus 1 terms, then A2 gets paired with n minus 2. So it's 1 plus 2 plus n minus 1 terms appear, which is just n choose 2. So we let dnk, little dn, be dnk raised to the power n choose 2 inverse. So for example, when n is 3, 3 choose 2 is 3, and we take the cube root of this number. But when n is 4, then there's 6 terms, and we take the 6th root of this number, and so on. And we, of course, we take the non-negative root of this number. And then finally, we define d infinity of k to be the limit as n goes to infinity of dn of k. And this is called a transfinite diameter. Okay. Okay, so we are going to study this transfinite diameter. And in fact, it will be the first of 3 different ways of measuring the size of k. We are going to have the quantity d infinity of k. We're going to also have a quantity r infinity of k, which I call the polynomial diameter or polynomial radius of k. And then there's going to be a third quantity called the capacity of k. And we'll prove that all of these are equal. But they have very different descriptions, and the interplay between these 3 equal ways of measuring the size of a compact set in the plane is very powerful. Okay, so let's start by looking at the transfinite diameter in more detail. Now there's a beautiful way to think of this product here. This product comes up all the time. For example, suppose the a1 up to an were the roots of a monic polynomial. What would the product of the differences of the roots be? Hint, it vanishes when the polynomial has a multiple root.
The discriminant.
The discriminant, very good. So this quantity is very closely related to the discriminant of the corresponding polynomial. And the discriminant has a natural square root once we've chosen an ordering for the roots, and this is called the Vanderbilt determinant. So let's stop with this for a second and discuss the Vanderbilt determinant. So this is a beautiful idea. And as we're seeing, it's connected to both geometry and algebra. And it's the following. So given A1 up to AN in the complex plane, we define V of A1 up to AN to be the determinant of the following matrix. So you put ones in the first column, and then in the second column, you put your numbers, A1, A2 up to AN. So this is going to be an n by n matrix. And now in the next column, you put A1 squared, A2 squared, A3 squared. So you put the squares of your numbers, and you keep going. You put the cubes and the fourth powers, and then at the very end, since this is n by n, you have an to the n minus 1, sorry, a1 to the n minus 1, a2 to the n minus 1, down to an to the n minus 1. Okay, now here's a beautiful fact about the Vanderbilt determinant. This is in fact equal to the product over I less than j of aj minus ai. That's an identity in algebra over the integers. So it has nothing to do actually with the complex field. It would be true in any field of characteristic 0, maybe even other characteristics. I haven't thought about that case. And so we get this beautiful formula for this product as the absolute value of a big determinant. And that's very useful because there's lots of ways of expressing and bounding determinants. And then as I mentioned, if you wanted, the one issue with this quantity is if you were to switch A1 and A2, then two of the rows would switch and the Vanderbilt determinant would change sign. But its square doesn't depend on the order of A1 up to AN. So B of the AI squared turns out to be the same as the discriminant of the polynomial P of Z, which is the product of Z minus AIs. Okay, so this is a theorem here. The Vanderbilt determinant is given by this formula. Okay, now first, why should this formula be true? The reason it should be true is very simple. When does this side vanish?
Like when two of the rows of the matrix are the same.
Yes, exactly. So this side vanishes if and only if two of the numbers AI are the same. And that happens if and only if two of the columns of the matrix, two of the rows of the matrix happen to be identical. If A1 equals A2, these two rows are the same. So of course the determinant vanishes. So one way to prove this theorem is to say, well, this is a polynomial in n variables. This is also a polynomial in n variables. And this factor has to divide this polynomial because this polynomial vanishes when this one does. And so using unique factorization of polynomials, you get equality up to some constant, and then you check that the constant is 1. But I want to give you a much better proof of this fact that makes the Vanderbilt determinant more conceptual. So whenever you have a determinant, you have a matrix, and you should think of that matrix as a linear map. So what is the linear map associated to the Vanderbilt determinant? Well, given these numbers AI, we have a map from, let me take it, CZ to the n minus 1. So these are polynomials, P of Z, with a degree of P less than or equal to n minus 1. So this is an n-dimensional space. And then we have a map, an evaluation map determined by A to C to the n. and it sends a polynomial p of z to p of a1 up to p of an. And I claim that the Vanderbilt determinant is just the determinant of this linear map. Well, wait a sec, but to define a determinant, you need to have a basis to get this matrix, or you need to choose a volume form on this side. And we already have coordinates here, so that's fine. But to write this down as a matrix, we need to choose a basis for this side. So the observation is that V of A is the determinant of EV A for the basis. P0 of Z is 1, P1 of Z is Z, Pn minus 1 of Z is Z to the n minus 1 for the space of polynomials, CZ n minus 1. So in other words, it's the determinant of the matrix, which is Pj evaluated on AI. Of course, the indices are slightly weird. The i's go from 1 to n, the j's go from 0 to n minus 1. It's still an n by n matrix. So to compute the Vanderbilt determinant, intrinsically, we had to choose a basis for the polynomials. But there was an obvious basis to choose. Okay, but now we come to an interesting observation. Which is, so now for the proof, what we note is that in fact, V of A is the determinant of the matrix Pj AI for any sequence of monic polynomials with a degree of Pj equal to j. J goes from 0 up to n minus 1. We didn't have to use 1z, z to the n minus 1. We could have used any polynomials we like as long as they were monic. And the reason for this is that let's think about what happens when you change your basis from, if you want to express a sequence of monic polynomials in terms of this standard basis. So that's because if we were to take this column vector of polynomials, P0 up to Pn minus 1, this would be equal to some matrix times the polynomials 1z, z squared up to z to the n minus 1. And what would it look like? Well, the first polynomial is just has to be 1. There's only one polynomial of degree 1. So this is 1 and then all zeros here. The next polynomial has to be monic of degree 1. So it's allowed to involve 1 and z, but it's not allowed to involve any of these higher order terms. And the coefficient of z has to be 1. So it's 1 and something, and then zeros here. And so the change of basis between a sequence of monic polynomials and the standard basis is given by an lower triangular matrix with 1s on the diagonal. And the determinant of this is equal to 1. So if you change basis from these polynomials to these polynomials, you don't change the determinant. Okay, now how can we use that to prove this theorem? So we could, for example, let Pj of z be equal to z minus a1, z minus a2 up to z minus aj. That's certainly a monic polynomial of the correct degree. And then with respect to that basis, we get that VA is the determinant of, and now let's think of what we're going to put in. We're going to get, first we're going to have, in the first column, we're going to have P1 of AI and P0 of AI. P0 is 1, so we got 1s. Then the next column, we're going to have P1 of AI. That's just this polynomial here. It's Z minus A1. And so when we plug in A1, we're going to get 0. When we plug in A2, we're going to get A2 minus A1. Then A3 minus A1, and so on. When it comes to the next column, P2 of AI, this will vanish for both A1 and A2. And then when it comes to A3, we'll get A3 minus A1 times A3 minus A2. And so on. So once again, we get an upper triangular matrix, a lower triangular matrix, and the determinant is the product of the diagonal entries, and the product of the diagonal entries is this product here. So that's the proof that the Vanderbilt determinant is given by this simple product, and it reveals a lot more about what the determinant is measuring. Okay, so now we will be able to use this in our analysis of the transfinite diameter because we now have an expression for dn. dn is just equal to the absolute value of the determinant of v of a1 up to an, or rather it's the dn is equal to the max of this determinant, the absolute value of this determinant, with AIs in our compact set K. Okay, so let's try to do an example. How about the unit circle? So if you want to put endpoints on the unit circle and make the product of their differences as big as possible, where do you think you might want to try putting them?
Roots of unity.
Yeah, why not try the nth roots of unity? So as an example, we could take AI, the nth root of unity to the ith power. In other words, e to the, I have an I everywhere. Okay, AK equals e to the 2 pi I k over n. So just put these points evenly spaced on the unit circle. I wonder what this gives for the value of dn. I know how to find out. I'll have you figure it out. So let's have a brief breakout room for 5 minutes, and we try to figure out what the product of these differences is, or what this Vanderbilt determinant is in the case of the nth roots of unity spread out on the unit circle. The point being, of course, that in fact, the distances in question are not all the same. You have one here, and then you have these other roots, and you have to take the product of all of these different lengths. And in fact, you have to do that for every pair I less than j. So let's have a quick trip to the breakout rooms to work on this problem. And so I remind you, please introduce yourself when you arrive, pick a reporter, and then discuss this question. Okay, so here we go. And see you in 5 minutes. Okay, welcome back. So please raise your virtual hand if you're a reporter. Just go to reactions and click at the bottom where it says raise hand. So far, I only see one reporter. If you forgot to select a reporter, please volunteer as a reporter. Okay, so let's start with CJ. Tell us what you think.
So we only really got as far as identifying the roots of unity as the roots of the polynomial x to the n minus 1.
Okay,
So all we need to do is define the discriminant of that polynomial, and that should give us what we want. But that's kind of not that's not computationally less difficult, I think, than just doing it directly.
right, okay, good point. So certainly the polynomial x to the n minus 1 is important here, or z to the n minus 1. Let me go to another reporter. How about Henry? Do you have something to add?
So we looked at the matrix, the Vanderbilt Matrix,
Yeah,
and we noticed that it's actually like the rows are orthogonal to each other.
okay,
So, and that the magnitude of the the product of a row with itself is constant. I can't tell you what the constant is, but it's pretty easy to calculate.
okay,
It's like, I was just working it out just now, but once you determine that that value, then you take the product, you take that to the nth power.
very good. So we could also, let me ask for elaboration from Alec. Do you have something to add to the discussion?
Oh, I guess like the way I did it is like okay, let's just compute the product of all the terms involving 1. So that's
Okay,
like
okay.
1 minus zeta times 1 minus zeta squared.
Right. So here I drew the case n is equal to 5. So there's a lot of terms in the product 10, but you could look at the product of the distance from 1 to zeta, zeta squared, zeta cubed, and zeta to the 4th. Just these 4 numbers.
And then basically because the other roots of unity besides 1 are the roots of 1 plus x squared plus dot dot dot,
Yes.
the magnitude of this has to be n minus 1. So then if you raise this to the nth power and divide and take a square root, you get the magnitude.
Okay, so that's a good idea. So you're saying, let's look at the polynomial x to the n minus 1 over x minus 1.
Yeah.
So let's call that p of x, or pn of x. And if I look at, first, this is
It's 1 plus
x minus zeta squared up to x minus zeta to the n minus 1. But it's also 1 plus x plus up to x to the n minus 1. And if we look at p of 1, that'll be the product of 1 minus zeta to the I, where I goes from 1 to n minus 1. Well, what is p of 1?
Sorry, it's n, not n minus 1.
It's n, not n minus 1. But it's a great idea. So this gives you n, and then you have to work a little bit more to figure out what the product is as 1 varies through these other points. Did you get a final value for the determinant?
Oh, for each of the other values, like you're just multiplying by a root of unity, basically. So the magnitude doesn't change. So
Okay,
n to the n, like, and then you take a square root because you only want I less than j.
very good. So you could, so this squared is the same as the product over I not equal to j of zeta j minus zeta I. And by the argument you just gave, you can break this up as to a product over I of numbers that just come out in absolute value to be equal to n. And so this is n to the n. And so in fact, the Vanderbilt determinant is in absolute value n to the n over t. Great. Vinka, do you have something to add or tell us
Oh,
what?
yes. So if you look at the Vanderbilt matrix,
Yes.
and it turns out it's just like each row is going to be zeta to the ij, which is just the matrix for like the DFT. So its inverse is going to be like 1 over n times like the conjugate transpose. So as a result, you can like 1 over square root of this matrix, 1 over square root n of this times this matrix is going to be unitary, and thus has determinant 1.
Okay.
So the determinant of the original matrix would be square root n to the n.
Very good. And to the n over 2. So we even have consistency across groups. Okay, great. Very good. So there were two approaches, both of which are great. One is to use this idea that the nth roots of unity other than n themselves are given by this polynomial whose value at 1 tells you the sum of the terms in the Vanderbilt product. And the other idea is to look straight at the matrix. And one way to say it is, rather than, it's true that the columns, the rows are orthogonal, but also the columns are orthogonal, and they all have the same norm. And the norm is just the norm of this vector, which is all ones. And so the norm of a vector of all ones of length n is the sum of 1 squared to the 1/2, which is n to the 1/2. And since you have n such vectors, the determinant is n to the n over 2. Okay, so I want to highlight 2 things about this calculation. The first is that it was productive to think in terms of the rows of the Vanderbilt determinant, and in this case, the product of their norms of these vectors was an upper bound for this product. And there's a general theorem to that effect, which you know very well over the real numbers, but it's also true over the complex numbers. This is called Hadamard's theorem, or Hadamard's inequality. And it says that if you have a matrix M with rows V1, V2, up to Vn, this is a n by n complex matrix, then the absolute value of the determinant of M is less than or equal to the product of the norms of these vectors Vi from 1 to n. So over the real numbers, this is just saying that if you had, say, 3 vectors in R3, then the determinant of these 3 vectors would be bounded by the product of the 3 lengths. And of course, the product of the 3 lengths, I'm not drawing this very well, is an upper bound. Okay, let's draw 1 vector vertically, 2 horizontally. So we have a parallelogram in the horizontal direction, and then the determinant is the volume of this parallelepiped with 3 sides given by the 3 vectors. And so the volume of this pyramid, of this parallelepiped, is bounded by the lengths of its 3 sides. It's optimized when the 3 sides are orthogonal. Otherwise, you get an upper bound for the determinant. But that turns out to work as well over the complex numbers. And in the case of orthogonality, then equality holds. Okay, so with a little experience with Vanderbilt determinants, we should be able to address the theory of transfinite diameter somewhat more intelligently. But the first thing I'm going to prove actually doesn't require the Vanderbilt determinant at all. And that is, what I'd like to show is that the transfinite diameter exists. So remember that there's these numbers dn, which are characterized by the property that dn to the n of n choose 2 is capital Dn, which is the max product over I less than j. of aj minus ai. And I want to show that the limit exists. So the theorem is that dn plus 1 is less than or equal to dn. And as a corollary, d infinity of k, which is the limit of dn of k, is well defined. Now, one thing that's kind of interesting about this is that for the circle, it turns out that your calculation was in fact the best you can do for endpoints on the circle. So dn of S1 turns out to be n to the n over 2 as you calculate it. And notice that this is significantly bigger than 1. In fact, it goes to infinity as n goes to infinity. Nevertheless, the transfinite diameter is 1. And that's because n choose 2 is what? It's n times n minus 1 over 2. So if we take dn of S1 and we raise it to the power n choose 2 inverse, what we get is n to the n over 2 times 2 over n times 1 over n minus 1. So we get n to the 1 over n minus 1, and that luckily tends to 1 as n goes to infinity. So d infinity of the circle, the transfinite diameter of the circle, is 1. And it's a little strange. Why don't we call this the transfinite radius instead of the transfinite diameter so it agrees with the radius? Well, too late now. This is the terminology that's in common use. Okay, so let's see why the distances are increasing. So there's a kind of obvious reason why this should be true, which is that when you take a product with n plus 1 terms, inside of it you have products with n terms. And the products with n terms are bounded by dn because dn is the max of what you can get using just n numbers. So for the proof of the theorem, we let dn plus 1i be the usual product, the product over I less than j of ai minus aj, but with all terms involving I omitted, but with all terms involving, maybe I should call this super K, involving K omitted. So we can do that for K equals 1 up to n plus 1. Okay, so now let's look at the product of dn plus 1. So let me make a quick observation. So after you throw out the terms involving k, you're left with a product that looks like the product for dn. In fact, it's just what dn would be if you took the numbers from a1 up to n, crossed out the kth, and plugged them into the formula for dn. So this is certainly less than or equal to dn for all n. So now we just look at the product of dn plus 1 to the k, where k goes from 1 to n plus 1. And we ask ourselves, how many times does the term ai minus aj appear? So it appears in every product here except when k is equal to I and except when k is equal to j. So in this product, you see ai minus aj raised not to the power n plus 1, but to the power n minus 1. And so what this gives is exactly dn plus 1 to the power n minus 1. On the other hand, there's n plus 1 terms, and each is bounded by dn. So this is less than or equal to dn to the n plus 1. Okay, now what is this quantity here? Well, let's let me write this as little dn plus 1. And then this is little dn plus 1 raised to the power n plus 1 choose 2, and then further multiplied by n minus 1. And on this side, we have little dn to the n choose 2 raised to the power n plus 1. Well, those are the same. This is n times n minus 1 times n plus 1 over 2. And this is n plus 1 times n over 2 times n minus 1. So the exponents are the same, and these are less than or one's less than or equal to the other, and therefore dn plus 1 is less than or equal to dn. Okay, so as you are allowed to take more and more points, the transfinite diameter decreases, and so it actually has a limit. Okay. So that's at least we have something that's well defined. But how are we ever going to compute it? Well, one answer you've already seen. If you choose some points, you get lower bounds for the transfinite diameter. So how to compute the infinity of k? And what we see is that explicit choices of ai give lower bounds on d infinity of k. And now we're going to meet a situation that's very common in conformal invariance, which is we're going to formulate a kind of dual problem. And for the dual problem, explicit choices will give upper bounds. And so if you can find explicit choices that give good lower bounds and explicit choices that give the same value for the upper bound, then you've computed the transfinite diameter. So we want a variation of the diameter, which is somehow similar in spirit, but which gives where we can get explicit upper bounds. So we want something where the max is replaced by a min. And this is what's called the polynomial diameter. Or at least I call it the polynomial diameter. It doesn't seem to have a well-defined name, but let's say what the definition is. What we do is we set Rn of k to be the minimum over p of the maximum over z and k of the absolute value of p of z, where p ranges in monic polynomials, we call it Pn, of degree n. So what you try to do is you try to make what you're really trying to do, this expression here, the maximum over z of k of Pn, that's just a measure of the size of Pn applied to k. So you have your set k, and you apply a polynomial that's monic of degree n. So it's z to the n plus a1 z to the n minus 1, etc., plus lower order terms, and k gets sent to something else. And then you look at the smallest ball, which contains the image, the smallest ball around the origin, which contains the image. And the smallest you can make the image is this quantity Rn. Now, because of the way that the fact that we've taken the image of the harmonic polynomial, if you multiply by, if you take z and you scale by t, this is no longer monic. Its leading term is t to the n, z to the n. So you have to scale by t to the minus n to keep this monic. So this quantity r to the n turns out to be homogeneous of degree n rather than degree 1. And so as before, we define Rn of k to be the degree 1 version, which is Rn of k to the 1 over n. And so then the main theorem is that, well, first, the limit of Rn of k as n goes to infinity, which we'll call R infinity of k, exists, and it's equal to d infinity of k. And now we examine the definition and we see that whenever we give explicit values for Pn, we get upper bounds on Rn of k, because Rn of k is the minimum for overall Pn. So explicit Pn give upper bounds to the minimum. So explicit choices of Pn give upper bounds on d infinity. And so if you can find explicit choices of Pn that agree with the upper bounds you're getting from explicit choices of AI, then you've computed the transfinite diameter. So for example, again, if we take k to the S1, we can just take Pn of z to the n. And on the unit circle, the maximum of this polynomial is 1. So that shows Rn of k is less than or equal to 1. And therefore, R infinity of k is less than or equal to 1. But we already proved that d infinity of k is greater than or equal to 1. Therefore, the transfinite diameter of the circle is exactly 1. Okay, so next time we'll discuss the equality between these two measures of the size of a set. And then finally, we'll relate this all back to harmonic functions and the Green's function to reconnect with complex analysis. Okay. So as always, I'll hang around after stopping the recording.